Our universe has a birthday. We know this because science has pieced together its origin story, a tale told in faint light and ancient echoes. That story rests on two incredible ideas: the Big Bang and cosmic inflation. These are the pillars holding up our modern understanding of everything, from the largest galaxy to the smallest particle. By the end of this journey, you will know the 25 specific discoveries that built this cosmic epic from a wild speculation into our best picture of reality. How did everything begin from almost nothing, and why is the universe so perfectly tuned for existence? The answers are more mind-bending than any fiction. What does it feel like to finally hear the universe's first whisper? The story of this discovery begins not in a grand observatory, but at a humble horn antenna in New Jersey. In 1965, two radio astronomers named Arno Penzias and Robert Wilson were troubleshooting a persistent problem. Their sensitive equipment was picking up a faint, annoying hiss, a uniform microwave static that came from every direction in the sky, day and night. They scrubbed the antenna clean of pigeon droppings, checked every connection, but the noise would not go away. It was, as they famously described, an excess antenna temperature. What they had stumbled upon completely by accident was the oldest light in the universe. This faint glow was the cosmic microwave background, the cooled and stretched remnant of the universe's fiery birth. It is the direct afterglow of the Big Bang itself. To understand why this is so monumental, picture the early universe as a dense, searing hot soup of particles and energy. For its first 380,000 years, it was so hot and thick that light could not travel freely. It was constantly scattered by free electrons, like trying to see through a dense, glowing fog. Then, as the universe expanded and cooled, electrons combined with protons to form the first neutral atoms. Suddenly, the fog cleared. That primordial light, released in that moment of transparency, has been traveling across the cosmos ever since, stretched by the expansion of space into the microwave radiation Penzias and Wilson detected. This discovery was a direct, observational snapshot of the infant universe, a baby picture taken when it was a mere 380,000 years old. It provided the first undeniable, rock-solid evidence for the Big Bang theory. Before this, competing ideas like the steady-state theory, which proposed the universe had no beginning and was eternally creating new matter, were still plausible. But the cosmic microwave background was a relic of a specific hot, dense past. It was the echo of a definite beginning, and it changed cosmology forever. The universe had spoken, and its first whisper was a microwave hiss. That faint cosmic hiss was just the beginning. To truly understand what it meant, scientists needed to dissect its light with incredible precision. And when they did, they found something profoundly elegant. The cosmic microwave background radiation does not just come from all directions. It has a very specific, perfect quality to its glow. Its spectrum, the precise distribution of energy across different wavelengths, matches what physicists call a perfect blackbody. Think of a blackbody as an idealized object that absorbs all radiation that hits it and then re-emits it with a characteristic signature based solely on its temperature. A hot piece of iron glowing red, then orange, then white as it heats up is a rough, everyday example. The specific curve of light it gives off is its blackbody spectrum. For decades, the Big Bang theory predicted that the universe's early fireball state would have been in perfect thermal equilibrium, creating a glow with this exact, flawless blackbody shape. But measuring it from Earth through our atmosphere was nearly impossible. The theory's prediction hung in the balance. Then, in 1989, NASA's Cosmic Background Explorer satellite COBE was launched. Its instruments, far above the distorting effects of our atmosphere, measured the CMB spectrum with unprecedented accuracy. The results were breathtaking. The data points fell perfectly on the predicted blackbody curve. The match was so exact, with deviations smaller than 1 part in 10,000, that the lead scientist, John Mather, famously presented the results by simply showing the theoretical curve with the experimental data overlaid. The room of astrophysicists erupted in a standing ovation. This was discovery number 2, and it was a monumental triumph. That perfect blackbody spectrum was the smoking gun. It confirmed that the early universe was indeed a hot, dense, and uniform soup in a state of near-perfect thermal equilibrium, just as the Big Bang model described. Every particle was constantly interacting, bouncing off one another, creating a smooth, even glow before the fog cleared. Alternative theories, like the steady-state model, could not naturally produce such a perfect, pristine blackbody signature from all over the sky. They might have predicted a mishmash of different temperatures and spectra. The universe's first light was not messy or patched together. It was a single, pure note from a symphony of unimaginable heat. This perfection told us the infant cosmos was a far simpler and more uniform place than it is today. But that very perfection would soon lead to an even deeper mystery, a puzzle written into the light itself. That perfect blackbody glow presented cosmologists with a paradox so deep it threatened to unravel the entire Big Bang story. The problem was not the light's quality, but its shocking uniformity. When scientists created detailed maps of the cosmic microwave background, they found its temperature was the same everywhere to an astonishing degree, fluctuating by less than 1 part in 100,000. This sounds like a good thing, a sign of a smooth, orderly beginning, but according to the standard Big Bang model, it was actually impossible. This is known as the horizon problem. To understand why, think about the speed of light as the universe's ultimate speed limit. Nothing, not even information or heat, can travel faster. In the standard Big Bang timeline, the universe was about 380,000 years old when it released the CMB light we see today. In all that time, light could only have traveled a finite distance. This creates a cosmic horizon, a maximum sphere of influence around any point. Now, look at 2 spots on opposite sides of the sky. Their CMB light has taken almost 14 billion years to reach us, coming from regions that were vastly far apart when the light was emitted. When we trace their paths back to that moment 380,000 years after the Big Bang, we find a stunning fact. Those 2 regions were so far apart that light, traveling at the cosmic speed limit, would not have had enough time to move between them. They were outside each other's horizons, completely causally disconnected. They had never been in contact, never been able to exchange heat or information to balance their temperatures. It is as if you had 2 people in separate, soundproof rooms on opposite sides of a vast concert hall, and without any communication, they both began to sing the same song at the exact same pitch and tempo. How could they possibly coordinate that? In the standard Big Bang, there was no mechanism for the entire observable universe to reach this perfect thermal equilibrium. The hottest and coldest parts should be wildly different, reflecting separate, unconnected histories, yet the CMB tells us they were virtually identical. This was not a minor detail, it was a fundamental flaw. The universe, in its first baby picture, looked impossibly uniform. The Big Bang model, for all its success, could not explain its own smoothest feature. Scientists were faced with a choice. Either the universe began in a state of inexplicable, fine-tuned uniformity by pure chance, or something dramatic happened in its first fleeting moments to force everything into harmony. The stage was set for a revolution, a concept so radical it would rewrite the first chapter of cosmic history in a fraction of a second. The universe's impossible smoothness was not its only mysterious feature. A second, equally profound puzzle was hiding in the geometry of space itself, a problem of cosmic balance called the flatness problem. To grasp it, we must think about the shape of the entire cosmos. According to Einstein's theory of general relativity, the mass and energy in the universe dictate the large-scale geometry of space. This geometry can take one of three possible forms. Space could be positively curved like the surface of a sphere where parallel lines eventually meet. It could be negatively curved like a saddle where parallel lines diverge. Or it could be perfectly flat like a sheet of paper where the classic rules of geometry we learned in school hold true. For a long time, this was a deep theoretical question. But then, observations of the cosmic microwave background gave us a way to measure it. By studying the apparent size of temperature fluctuations in that ancient light, scientists could determine the universe's geometry. The answer, when it came, was startlingly precise. Our universe is flat, or so nearly flat that our most sensitive instruments cannot detect any curvature at all. This sounds simple, even logical, but in the context of the classic Big Bang model, it is a condition of breathtaking instability. Think of the universe's density as a critical balancing point. For space to be flat, the actual density of matter and energy must exactly match a specific critical value. If the density were even slightly higher at the beginning, gravity would have quickly caused the universe to collapse back in on itself in a big crunch. If it were even slightly lower, the universe would have expanded so rapidly that matter would have flown apart before galaxies could ever form. In the standard model, as the universe ages, any tiny deviation from perfect flatness at the beginning gets wildly magnified over time. To be as flat as we see it today, some 14 billion years later, the universe's initial density had to be fine-tuned to an absurd degree, perhaps to 1 part in 10 to the 60th power or more. It is the cosmic equivalent of balancing a pencil perfectly on its tip at the moment of creation, and expecting it to remain standing untouched for billions upon billions of years. Not a single gust of wind, not a single vibration could disturb it. This degree of perfection defied belief. It suggested the universe did not just happen to be flat by lucky accident. Something must have actively forced it into that precise condition. The flatness problem, together with the horizon problem, showed the classic Big Bang was incomplete. It described the expansion of the universe beautifully, but it could not explain why the universe began in such an exquisitely tuned, improbable state. These were not minor gaps in the theory, they were foundational cracks. The cosmos was practically shouting that its first moments contained a physics we had not yet imagined, a mechanism that could smooth out irregularities and lock in perfect flatness in an instant. The answer, when it arrived, was more extraordinary than anyone had dared to predict. The universe's impossible perfection demanded a radical new physics. That demand was answered in 1981 by a young physicist named Alan Guth, who proposed a breathtakingly simple yet profound idea: cosmic inflation. Imagine the very first moment of time, a fraction of a second after the initial singularity. According to Guth's theory, the universe was filled with a strange, exotic form of energy that acted like a powerful repulsive force. This energy did not push matter apart, it caused space itself to expand at an unimaginable rate. We are not talking about the steady, stately expansion we see today. Inflation was exponential, a runaway process where the size of the universe doubled, and then doubled again, over and over, in intervals so brief they are measured in tiny fractions of a second. In less time than it takes to blink, a region of space smaller than a single proton could have been stretched to a size larger than our entire observable universe. This single, violent event solves the twin mysteries of horizon and flatness with elegant simplicity. First, the horizon problem. Remember those two disconnected patches of sky with the same temperature? Before inflation, they were part of a single, tiny, causally connected region. Every particle in that microscopic seed was in thermal contact, able to share energy and smooth out any differences. Then inflation happened. It took that tiny, uniform patch and stretched it to cosmic proportions, far larger than the entire sky we see today. The perfect smoothness was imprinted on that seed, then blown up to the size of the cosmos. The reason the universe looks uniform is because our entire observable universe came from a single, harmonious speck. Second, the flatness problem. Think of space having a certain curvature like the surface of a balloon. Now inflate that balloon to the size of the Earth or even the solar system. As you stretch it to an enormous scale, any small bump or wrinkle on its surface becomes vanishingly small. From your local perspective, the surface appears perfectly flat. Inflation does exactly this to the geometry of the universe. It takes any initial curvature and stretches it so dramatically that, from our limited viewpoint within it, space appears perfectly flat. It forces the universe toward that critical density balance, locking in the flatness we observe. Inflation was not just a patch for the Big Bang, it was a complete rewrite of its first chapter. It proposed that the universe we know was born from a microscopic quantum fluctuation, then inflated to macroscopic size in an instant, creating a smooth, flat, and vast canvas upon which all later history, from the formation of galaxies to the emergence of life, would be painted. It was a theory of breathtaking audacity, but a theory needs evidence. Could we find proof of such a fleeting, violent event from the dawn of time? But inflation did more than just smooth and flatten the cosmos, it also gave it texture. The same violent expansion that erased large-scale irregularities had to leave behind a faint, fundamental imprint, a whisper of its own quantum origin. This leads us to discovery number 6, the idea that all the grand structure of the universe grew from the tiniest possible seeds, quantum fluctuations. To understand this, we must shrink our perspective down to the microscopic realm that ruled the universe during its first fraction of a second. The energy field that drove inflation was not a perfectly smooth, placid lake. On the quantum scale, it was a seething, foaming sea. Heisenberg's uncertainty principle tells us that empty space is never truly empty. It is a roiling cauldron of virtual particles popping in and out of existence. These are quantum fluctuations, temporary bubbles of energy that appear and vanish in an instant. In the normal world, these fluctuations are immeasurably small and fleeting. But inflation acted like a cosmic amplifier of unimaginable power. Picture a tiny ripple on a pond, smaller than an atom. Now imagine the pond's surface suddenly and violently expanding to the size of an ocean in less than an eye blink. That microscopic ripple would be stretched to the size of a continent. This is precisely what happened during inflation. Those fleeting quantum ripples in the inflationary energy field were frozen in place and stretched to astronomical scales. Where the field had a tiny, random bump of slightly higher energy, inflation stretched it into a vast region of slightly greater density. Where there was a dip, it created a vast underdense region. These imperfections were no longer quantum ghosts. They became real, classical variations in the density of the universe, imprinted directly onto the fabric of space-time itself. This is the profound link. Those stretched quantum fluctuations became the gravitational seeds for everything that followed. After inflation ended, the universe was almost perfectly smooth, but not quite. It was imprinted with these faint blueprints, these tiny hills and valleys in the density of matter and energy. Gravity got to work over billions of years, relentlessly pulling matter into the denser hills. Gas pooled, clouds collapsed, and the first stars ignited. The underdense valleys became the great cosmic voids we see today. Every galaxy cluster, every spiral arm, every star, and ultimately every planet and person owes its existence to those microscopic quantum jitters magnified by inflation. It provides the first physical mechanism that takes the weird, probabilistic rules of the quantum world and transforms them into the definite, classical reality of stars and galaxies. The grand cosmic web we see in galaxy surveys is not random. It is the grown-up version of quantum noise from the first moment of time. This means the largest structures in the cosmos were literally sown by the smallest events physics allows. Our entire universe, in all its splendor, is a quantum fluctuation writ large across the heavens. Those quantum seeds were not just a theoretical idea, they came with a precise, testable prediction written across the sky. If inflation was correct and had stretched those microscopic ripples into cosmic blueprints, then those blueprints should be visible in the universe's first light. The cosmic microwave background could not be perfectly smooth. Imprinted upon that near-uniform glow, there had to be incredibly subtle variations in temperature, tiny hot and cold spots corresponding to those initial density hills and valleys. Inflation's calculations were specific. It predicted these anisotropies, these deviations from perfect uniformity, should exist at a level of about 1 part in 100,000. This was not a random guess, it was a direct consequence of the physics of the inflationary expansion itself. The theory stated that the universe began with quantum jitters, and those jitters, magnified to cosmic size, would create a characteristic pattern of wrinkles in the fabric of spacetime just as the CMB was being released. Finding these specific wrinkles became the holy grail of cosmology. It was a breathtakingly bold forecast. Scientists were saying that by looking at the oldest light, they could see the amplified ghost of quantum mechanics from the first sliver of a second after the beginning. But for over a decade, it was a prediction in search of proof. The expected signal was incredibly faint, a whisper buried under cosmic static and instrumental noise. The technology of the 1980s simply was not sensitive enough to detect variations at that minuscule level. Every experiment that looked came back with results consistent with a perfectly smooth background, which only deepened the mystery. The tension was immense. On one hand, inflation elegantly solved the horizon and flatness problems. On the other, its key prediction about the CMB's texture remained unverified. If those anisotropies were not found at the predicted level, the entire beautiful theory could collapse. Cosmologists lived in a state of suspended animation, knowing that the answer was written in the microwave sky, waiting for an instrument precise enough to read it. The fate of our understanding of the universe's first moment hinged on finding variations smaller than 1 part in 100,000 in a faint glow from the edge of time. It was a waiting game, a race to build a machine that could listen more closely to the echo of creation than ever before. The long wait ended on a spring day in 1992. At a press conference in Washington, D.C., the science team from the COBE satellite, led by astrophysicist George Smoot, presented a map that changed everything. It was not a colorful image of galaxies or nebulae, but a blotchy, pixelated sky map of the cosmic microwave background. And across that map, like the faint texture of an orange peel, were the variations everyone had been searching for. The satellite had detected the primordial ripples, temperature anisotropies at the level of about 1 part in 100,000, exactly as inflation had predicted a decade earlier. The relief and excitement in the scientific community was explosive. It was the moment cosmology grew up. We had moved from a smooth, featureless baby picture to a detailed ultrasound showing the very fingerprints of creation. Smoot famously told reporters that if you were religious, it was like looking at the face of God. The poetic weight of that statement captured the profound awe of the discovery. This was not just another data point, it was the first direct observational evidence that the inflationary paradigm was on the right track. Those tiny hot and cold spots were the imprints of the quantum seeds, stretched to cosmic size by that violent early expansion. Inflation was no longer just a clever mathematical fix for the Big Bang's problems. It was a predictive framework that had just passed its most critical test. The map showed the universe was not just born smooth, it was born with a specific, fundamental kind of roughness, a pattern written by quantum physics and cosmic expansion acting in concert. For scientists, it was the moment the theoretical scaffolding of inflation solidified into a foundation. The universe had shown us its blueprint, and for the first time we could read it. Those primordial ripples in the cosmic afterglow were more than just a theoretical triumph. They were a set of blueprints, and like any good blueprint, it predicted what would be built. The hot and cold spots in the CMB were maps of slightly denser and thinner regions in the early universe. Gravity is a patient architect, and over billions of years it got to work on those plans. The slightly denser spots, where there was a tiny bit more matter, had a slightly stronger gravitational pull. They began to attract more gas from their surroundings, growing richer and denser over cosmic time. The thinner regions, meanwhile, were slowly emptied out as matter flowed toward the denser knots. This gravitational tug of war, operating on the colossal canvas of an expanding universe, sculpted the grand architecture we see today, the cosmic web. This vast, three-dimensional tapestry is not a random scattering of galaxies. It is an intricate network of massive filaments or walls of galaxies intersecting at dense clusters, surrounding enormous, nearly empty voids that can span hundreds of millions of light-years. It looks like the frothy structure of a sponge or a neural network on a cosmic scale. This is the universe's large-scale structure, and mapping it has been one of the great observational quests of modern astronomy. Projects like the Sloan Digital Sky Survey have painstakingly charted the positions of millions of galaxies, creating three-dimensional maps that reveal this breathtaking filamentary web in stunning detail. But here is the profound connection, the true test of our cosmic story. The specific statistical pattern of this grown-up web, the sizes of the clusters, the lengths of the filaments, the dimensions of the voids, is not arbitrary. It carries the exact signature of those initial quantum seeds from inflation. Scientists can take the pattern of anisotropies measured in the infant universe by COBE and later missions, run it through the known laws of physics and gravity in a supercomputer simulation, and fast-forward the expansion of the universe over 13.8 billion years. When they do, the result is a simulated cosmic web that looks, in its statistical properties, identical to the one we actually observe through our telescopes. The theoretical predictions derived from the CMB's tiny temperature variations match the observed distribution of galaxies with remarkable precision. This is a cross-check of monumental importance. It means the same physical model, starting with quantum fluctuations stretched by inflation, successfully explains two completely different snapshots of the universe, taken billions of years apart. The first snapshot is the smooth, hot plasma of 380,000 years after the Big Bang. The second is the clumpy, galaxy-filled universe of today. The theory bridges them perfectly. It tells a single, consistent story from the first quantum whisper to the grand celestial cities we see now. The universe did not just leave us one clue, it left us two, separated by almost all of time, and they tell the same story. This consistency is a powerful, independent validation that we are on the right track, that the inflationary Big Bang model is not just a story of the beginning, but a reliable narrative for the entire history of the cosmos. The cosmic web is a testament to gravity's patient work, but gravity is not the only sculptor at work in the universe. In the late 1990s, two independent teams of astronomers made a discovery so shocking it turned our cosmic timeline on its head. They were using distant supernova, specifically a type called Aya, as cosmic mile markers. These stellar explosions are remarkably consistent in their intrinsic brightness, making them perfect standard candles. By measuring how dim they appeared from Earth, astronomers could calculate their distance with great accuracy. By then measuring the redshift of their light, which tells us how much the universe has stretched since the explosion, they could chart the expansion history of the cosmos. Everyone expected to see the expansion slowing down, pulled by the relentless brake of gravity from all the matter in the universe. The only question was whether it would slow enough to eventually reverse in a big crunch or just coast toward a gradual halt. The data told a different story entirely. The most distant supernova, whose light had been traveling for billions of years, were fainter than they should have been. This meant they were farther away than expected. The only explanation was that the expansion of the universe was not slowing down at all. It was speeding up. Some mysterious repulsive force acting against the pull of gravity was pushing galaxies apart at an ever-increasing rate. This was the discovery of the accelerating universe, and it demanded a new ingredient in our cosmic recipe: dark energy. Think of dark energy as a property of empty space itself. Unlike matter, whose gravitational pull weakens as the universe expands and thins out, dark energy's repulsive push remains constant, or may even strengthen as space stretches. This means that as the universe gets larger, there is more empty space, and thus more of this repulsive force. Gravity dominates locally, binding galaxies and clusters, but on the vastest scales, dark energy takes over as the driver of cosmic destiny. This discovery, while concerning the universe's late-time evolution and not its birth, is a crucial pillar of our modern model, known as lambda CDM. It tells us the universe's story has three dramatic acts: a violent, inflationary beginning that set the stage, a long Middle Age dominated by gravity building galaxies and stars, and now a final era where dark energy is taking control, leading to a future of isolated galaxies in an ever-cooling, ever-expanding emptiness. The force that began inflation may be gone, but a different form of repulsive energy has reawakened, writing the final chapter of our cosmic story. This cosmic recipe is written into the light of the Big Bang itself. The precise pattern of hot and cold spots in the cosmic microwave background is not just a map of seeds, it is a detailed ledger of the universe's contents. By analyzing the statistical properties of those wrinkles, scientists can perform a cosmic accounting, measuring exactly how much of each ingredient makes up our reality. The numbers are both precise and profoundly humbling. The universe is composed of roughly 5% ordinary matter, the atoms that make up stars, planets, and us. 27% is dark matter, the invisible gravitational glue that holds galaxies together, and a staggering 68% is dark energy, the mysterious force accelerating cosmic expansion. This is the modern cosmic budget, and it tells us a startling truth. Everything we have ever seen, touched, or studied in a laboratory, every element in the periodic table, every mountain and ocean and living creature, accounts for a mere 5% of the total cosmic pie. We are a rare and precious afterthought in a cosmos dominated by invisible forces we do not yet fully understand. This precise breakdown is not a guess, it is a rigorous measurement extracted from the CMB data, cross-checked by observations of galaxy clusters and the large-scale structure of the universe. The way those primordial ripples subtly shift and stretch under the influence of gravity and pressure in the early plasma is exquisitely sensitive to the amounts of matter and energy present. It is like listening to a bell ring. The specific tone and overtones tell you exactly what the bell is made of. The universe's first light rings with a tone that reveals its composition. And here is where the story comes full circle. These specific ratios, this 5-27-68 split, are not just numbers we measured. They are a successful prediction of the combined model of inflation and the lambda CDM universe. The theory that began with a quantum seed and an explosive stretching, then added dark matter and dark energy to its later chapters, mathematically predicted that the CMB should look exactly the way it does given these proportions. When we plug those numbers into our simulations of cosmic evolution, from the first fraction of a second to the present day, they produce a universe that matches our observations in stunning detail. So the cosmic recipe is more than a list of ingredients, it is a profound validation. It tells us that our model, built piece by piece from the discovery of the CMB's glow to the detection of its ripples and the acceleration of expansion, is coherent and consistent. The universe has handed us its budget, and our theory of its history can balance the books. The universe's budget was locked in by those quantum seeds, but their pattern holds an even more specific signature. That pattern is not random noise, it follows a precise mathematical rule, a fingerprint left by the physics of inflation itself. This fingerprint is called the spectral index. Think of the primordial fluctuations as a cosmic chord, a note played across all scales of the universe, from the size of a galaxy cluster down to a single star system. The spectral index tells us how the volume or strength of that chord changes as you move to higher and lower pitches, from large scales to small ones. In a perfectly scale invariant universe, the strength of the fluctuations would be exactly the same whether you looked at a region 1 billion light-years across or 1 million light-years across. This would give a spectral index of exactly 1. But inflation, in its elegant simplicity, predicts something more nuanced, because the inflationary expansion was not perfectly constant, but gradually slowing as the energy field decayed. It left a subtle mark. The process imprinted a slight preference, making the fluctuations a tiny bit stronger on larger scales than on smaller ones. The predicted spectral index should be slightly less than 1. Measuring this number became a critical test. If we found it to be exactly 1, many inflationary models would be in trouble. If it were significantly less than 1, it would point toward specific, simpler versions of the theory. This was a job for the most precise maps of the cosmos ever made. The Wilkinson Microwave Anisotropy Probe, WMAP, and later the European Space Agency's Planck satellite, spent years staring at the cosmic microwave background, measuring the temperature differences between those hot and cold spots with microscopic precision. They were not just making a picture, they were performing a statistical symphony analysis on the universe's first light. The result was a triumph of precision cosmology. The measured spectral index is approximately 0.965, a number unmistakably and confidently less than 1. This deviation, though small, is monumental. It matches the prediction of a wide class of straightforward inflationary models where a single energy field drove the expansion. It tells us that inflation did not just happen, it happened in a particular, smooth way. The spectral index is like finding a specific manufacturer's stamp on the quantum seeds themselves. It rules out whole families of more complicated or contrived theories and points us toward the simplest, most elegant explanations. In the faint wrinkles of the cosmic afterglow, we have read not just the fact of inflation, but the detailed logbook of its execution. That precise spectral index was a fingerprint from the very first moment, a detail confirming the nature of inflation's engine. But the theory made an even grander, more sweeping claim about the shape of all reality. Remember the flatness problem, that cosmic balancing act that seemed impossibly fine-tuned. Inflation promised to solve it by stretching the universe so violently that any initial curvature would be smoothed away, like stretching a crinkled balloon until its surface appears perfectly flat from within. This was a beautiful theoretical solution, but it demanded observational proof. We needed to measure the actual geometry of the cosmos on its largest scales. The tool for this monumental measurement was once again the pattern of hot and cold spots in the cosmic microwave background. Those spots have a characteristic apparent size, a typical angular scale that depends on the universe's geometry. Think of it like using the spots as a cosmic ruler. If the universe were positively curved like a sphere, light rays would follow converging paths, making the spots appear larger than they truly are. If it were negatively curved like a saddle, light rays would diverge, making the spots look smaller. Only in a perfectly flat universe would the spots appear at their true, intrinsic angular size. The team behind the Wilkinson Microwave Anisotropy Probe, WMAP, performed this measurement with exquisite care. They analyzed the statistical distribution of the spots, looking for a specific peak in the data that corresponded to the most common size of these primordial ripples. The location of that peak would reveal the geometry of the universe. After years of data collection and painstaking analysis, the answer was definitive. The peak in the data fell exactly where it should for a flat universe. The measurements revealed that space is flat too, within a stunning margin of error of just 0.4%. This was not a suggestion or a hint, it was a resounding quantitative confirmation. The universe's geometry is Euclidean, just as the geometry we learn in school. Parallel lines will never meet. The angles of a triangle add up to 180 degrees, and the cosmos on its grandest scale has no overall curvature. This direct measurement from the ancient sky was the final observational nail in the coffin for the flatness problem. It showed that inflation's dramatic solution was not just a clever idea, it was a physical reality. The violent stretching in that first fraction of a second did not merely suggest flatness, it actively manufactured it, ironing out any primordial wrinkles in space-time itself until the cosmos we inhabit became geometrically perfect. We are not living in a universe that lucked into this precise balance. We are living in a universe that was forged into flatness. Flatness was a geometric triumph, but inflation promised an even more spectacular echo. That echo would come not from the heat of the ancient light, but from its very polarization, a subtle directional property. Scientists began hunting for a specific, twisted pattern within that polarization known as B modes. This pattern would be the ultimate smoking gun, a direct imprint of primordial gravitational waves. To understand why, picture gravitational waves as ripples in the fabric of space-time itself. When massive objects like black holes collide, they send out these ripples, stretching and squeezing space as they pass. In 2015, the LIGO Observatory famously detected such waves from a stellar collision. But the gravitational waves from inflation would be a different beast entirely. They would have been generated by the violent quantum jitters of space-time during that explosive expansion, a tremor in the cosmos's very foundation. These waves would have left a unique, swirly signature on the polarization of the cosmic microwave background as it was forming. Finding that B-mode pattern would be like finding the fossilized vibrations of the Big Bang's engine, direct proof that inflation happened and a window into physics at energies a trillion times beyond what any particle collider could ever reach. The hunt reached a fever pitch in 2014. A team using a telescope at the South Pole called BICEP 2 announced a stunning result. They believed they had detected this primordial B-mode signal. The scientific world held its breath. It seemed like the final, crowning discovery was at hand. But extraordinary claims require extraordinary evidence, and further analysis, crucially incorporating data from the Planck satellite, revealed a sobering truth. The signal BICEP 2 saw was largely, if not entirely, caused by a more mundane source, interstellar dust within our own Milky Way galaxy. This cosmic dust, when magnetically aligned, can produce a similar swirly polarization pattern, mimicking the primordial signal. It was a masterclass in scientific caution. The initial excitement gave way to meticulous cross-checking, a process that ultimately strengthened the field's rigor. The hunt, however, is far from over. The search for primordial B-modes remains one of the most intense pursuits in cosmology. New experiments with ever more sensitive detectors are being deployed, designed to meticulously distinguish between the faint whisper of inflation and the foreground fog of galactic dust. Finding that signal would be the final, direct link to the universe's first violent moment, allowing us to hear the tremors of creation itself. The hunt for primordial gravitational waves continues, a testament to science's patient rigor. But while we search for echoes of the first instant, a quieter mystery has persisted for decades, one that challenges the perfection of our cosmic story in a different way. This is the lithium problem, and it reminds us that even our most successful models have unresolved edges. To understand it, we must travel back not to the first fraction of a second, but to the universe's first few minutes. After inflation ended and the cosmos cooled, it entered a brief, pivotal phase called Big Bang nucleosynthesis. For about 17 minutes, the entire universe was a nuclear fusion reactor hotter than the core of any star. Protons and neutrons, the building blocks of atomic nuclei, slammed together in the searing heat, forming the first light elements. This process did not have time to build anything heavy like carbon or iron. Instead, it forged the primordial abundance of hydrogen, deuterium, helium, and a tiny trace of lithium. The calculations for this process are remarkably precise, based on well-understood nuclear physics and the known density of matter from the CMB. And for the most part, the predictions are a stunning success. The amount of helium-4 we observe in the oldest stars and gas clouds matches the Big Bang prediction exactly. The observed deuterium, a heavy form of hydrogen, also lines up beautifully, serving as a sensitive probe of the cosmic density of ordinary matter. These agreements are pillars of the Big Bang model. But lithium is the outlier. The theory predicts that a specific isotope, lithium-7, should have been produced in a certain amount during those first minutes. When astronomers look at the oldest stars in our galaxy, stars that formed from nearly pristine gas and should preserve that primordial lithium, they find only about 1/3 of the predicted amount. The observed abundance is roughly 3 times lower than the calculations say it should be. This is not a small discrepancy, it is a glaring gap. The lithium problem tells us something is off. Either our understanding of nuclear physics in those extreme early conditions is incomplete, perhaps involving unknown particles or interactions, or something has been destroying lithium in these ancient stars over billions of years, though models of stellar interiors struggle to explain such efficient depletion. It could even point to new physics during or after nucleosynthesis itself. This puzzle is a powerful reminder that cosmology is not a finished book. It is a living field where precise predictions clash with meticulous observations, forcing us to question, refine, and sometimes search for entirely new ideas. The lithium problem is a loose thread in the tapestry of the Big Bang, a small but persistent whisper that the universe's first few minutes might still hold secrets waiting to be unraveled. Yet the lithium problem is not the only crack in our otherwise elegant cosmic model. A far more profound and pressing tension has emerged, one that strikes at the very heart of our understanding of cosmic expansion. This is the Hubble tension, and it is arguably the biggest unsolved mystery in cosmology today. The problem is deceptively simple. We have 2 brilliant, independent ways to measure how fast the universe is expanding right now, a number called the Hubble constant. Both methods are incredibly sophisticated and both give incredibly precise answers. The only trouble is those precise answers do not agree. Let us break down the 2 paths. The first method looks back to the early universe using the cosmic microwave background as its guide. The Planck satellite mapped the CMB in exquisite detail. Scientists then feed that snapshot of the infant cosmos into our standard model of cosmology, the lambda CDM model that includes inflation, dark matter, and dark energy. The model acts like a cosmic film reel, running the physics forward from that early state to predict what the expansion rate should be today. This early universe method gives a Hubble constant of about 67.4 kilometers per second per megaparsec. That mouthful means that for every megaparsec, a distance of about 3.3 million light-years, a galaxy appears to be moving away from us 67.4 kilometers per second faster due to cosmic expansion. Now, the second method looks at the late universe, the cosmos around us. Astronomers use what are called cosmic distance ladders. They start with nearby stars, whose distances we can measure with geometry, and use them to calibrate brighter objects like Cepheid variable stars. Those Cepheids are then used to calibrate even brighter objects like Type Ia supernova in nearby galaxies. Finally, they observe those supernovae in faraway galaxies. By knowing the supernova's true brightness and measuring how dim it appears, they can calculate its distance. Combining that distance with the galaxy's redshift tells us the expansion rate. This late universe method, championed by teams using the Hubble Space Telescope, gives a Hubble constant of about 73 kilometers per second per megaparsec. The difference seems small, only about 5 or 6 units, but given the phenomenal precision of each measurement with error bars of less than 1%, this discrepancy is statistically huge. It is not a minor glitch, it is a glaring inconsistency. Think of it like two world-class chefs using the same recipe to bake a cake. One chef uses a precise chemical analysis of the original ingredients. The other chef tastes the finished cake and measures its density. Both are experts and both are confident in their methods, but when they compare notes, one says the cake must have 1 cup of sugar, while the other insists it has 1¼ cups. The recipe cannot be right both ways. In cosmology, the recipe is our standard model. The fact that the early and late universe measurements disagree so strongly suggests something is missing from our model. Perhaps dark energy is not a constant, but has evolved in strength over time. Maybe dark matter has properties we have not accounted for, interacting in new ways in the early cosmos. There could even be a new, exotic particle from the dawn of time that subtly altered the expansion history. This tension is not a failure of science, it is science at its most exciting. It is a clear signpost pointing beyond our current understanding, a cosmic clue that the universe still has profound secrets to share about its own evolution. That Hubble tension is a crack in our cosmic timeline, a hint that the universe's story may have twists we have not yet read. But there is one chapter we know happened, a dramatic transition that ended the universe's long, quiet childhood and brought light to the cosmos. This is the epoch of reionization, the universe's first dawn. After the release of the cosmic microwave background, the cosmos entered a period often called the Dark Ages. The universe was expanding and cooling, filled with a fog of neutral hydrogen and helium gas, but utterly dark. No stars, no galaxies, no sources of light beyond the fading afterglow of the Big Bang itself. This peaceful darkness lasted for hundreds of millions of years. Then, in the densest knots of that primordial gas, gravity finally overcame pressure. The first protogalaxies collapsed, and within them, the very first stars ignited. These were not like the stars we see today. They were behemoths, hundreds of times more massive than our sun, burning ferociously hot and blue and living short, violent lives. Their intense ultraviolet radiation acted like a cosmic blowtorch. It flooded the surrounding space with high-energy photons that slammed into the neutral hydrogen atoms, which are simply a proton and an electron bound together. This ultraviolet light had enough energy to rip those electrons away, a process we call ionization. One by one, then in vast waves, these first stars and the black holes that followed their deaths began to tear apart the cosmic fog. Think of it as a great thaw. Isolated bubbles of ionized, transparent gas began to form around the first luminous objects. Over millions of years, these bubbles grew and merged, their edges eating into the neutral hydrogen like fire eating through a dry forest. Eventually, the bubbles overlapped completely, and the entire intergalactic medium became ionized once more. The universe had been reionized. This was not a gentle sunrise, it was a violent, patchy process that took hundreds of millions of years to complete. But how do we know this happened? We cannot see those first stars directly. Their light is far too faint after traveling over 13 billion years. Instead, we detect the shadow of this epoch. Our most powerful telescopes point at the most distant quasars, brilliant beacons powered by supermassive black holes in the early universe. As their light travels to us, it passes through the intergalactic hydrogen from that era. Spectrographs break that light into a rainbow, and scientists look for a specific signature, a thick forest of dark absorption lines. These lines are the fingerprints of neutral hydrogen atoms absorbing specific wavelengths of the quasar's light. The stunning finding is that for quasars beyond a certain distance, corresponding to a time before reionization was complete, this forest of lines becomes so dense it forms a complete block, a phenomenon called the Gunn-Peterson trough. It is as if a cosmic curtain of neutral hydrogen has been drawn. For closer, later quasars, the curtain is gone, the trough vanishes, telling us the hydrogen has been ionized and is now transparent. Furthermore, the subtle polarization of the cosmic microwave background carries an echo of this event. As the CMB light passed through the newly reionized gas late in its journey, the free electrons scattered it one last time, imprinting a specific, large-scale polarization pattern. By measuring this, satellites like WMAP and Planck could pin down when reionization likely occurred, pegging it as ending around 1 billion years after the Big Bang. So we have two completely independent lines of evidence, one from the shadows cast on distant quasars and one from the ancient glow of the CMB, telling the same story. The epoch of reionization was the universe's great awakening, the moment when the first structures sculpted by those quantum seeds finally switched on the lights, burning away the primordial fog and setting the stage for the transparent, star-filled cosmos we see today. That first dawn was a violent, patchy affair, but it left behind a cosmic rhythm more regular than any heartbeat. The universe's early plasma was not a silent soup, it was a roaring, pressurized fluid. In that searing heat before atoms formed, photons and baryons, the particles that would become ordinary matter, were tightly coupled. They pushed and pulled against the relentless grip of gravity. This created sound waves, immense pressure waves that rippled outward from every slight over density, those quantum seeds we discussed earlier. Think of dropping a stone into a pond, but where the pond is the entire observable universe and the ripples expand at a significant fraction of the speed of light. These were not sound waves as we hear them, but true oscillations in density and temperature that traveled through the primordial fireball. They raced outward until a critical moment, the release of the cosmic microwave background. When the universe cooled enough for atoms to form, the photons suddenly streamed free. The music stopped, the pressure waves froze in place, their final crests and troughs etched into the distribution of matter like a fossilized echo. This left a specific, measurable scale imprinted on the cosmos, a preferred distance called the sound horizon. It is the maximum distance those pressure waves could have traveled before the cosmic music faded. This scale, about 500 million light-years in today's universe, acts as a perfect standard ruler, and we can see it when we map the three-dimensional positions of millions of galaxies in surveys like the Sloan Digital Sky Survey. We do not see a random scatter. We find that galaxies are slightly more likely to be separated by this specific scale, the sound horizon, than any other distance. It manifests as a subtle statistical excess of galaxy pairs separated by about 500 million light-years. It is as if we dropped billions of stones into that early cosmic pond, and all the ripples froze at the same moment, leaving a faint, recurring pattern in the large-scale structure. This pattern is the baryon acoustic oscillation, or BAO. Its power as a tool is breathtaking, because we know the true physical size of this standard ruler from the physics of the early universe. We can use it to measure cosmic distances with phenomenal precision. By observing how this apparent scale changes at different eras of the universe, we can chart the expansion history with an independent method that does not rely on the cosmic distance ladder or the CMB. It is a direct geometric probe. The results are a resounding confirmation. BAO measurements from galaxy surveys align perfectly with the predictions of our standard cosmological model, the same model built from the CMB and supernova data. They provide a third, completely independent pillar of evidence for dark energy and the accelerating expansion. This fossilized echo from the universe's first 400,000 years has become one of our most trusted tools for measuring the cosmos, a rhythmic signature from the dawn of time that still structures the universe today. The rhythmic echoes of the early universe tell a story of harmony, but that harmony was not guaranteed. In fact, one of the most compelling reasons scientists were driven to consider inflation in the first place was to solve a glaring cosmic absence, a missing particle that should have been everywhere. This is the mystery of the magnetic monopole. To understand it, we need to step back into the unimaginable heat of the universe's first moments. In today's world, magnets are familiar. Every magnet has a north pole and a south pole. If you cut a bar magnet in half, you do not get isolated poles. You get two smaller magnets, each with its own north and south. This is a fundamental feature of our electromagnetism. But many of the grand theories that attempt to unify the fundamental forces of nature, ideas called grand unified theories, make a startling prediction. In the extreme energies of the early universe, just a fraction of a second after the Big Bang, the forces we know as electromagnetism and the weak and strong nuclear forces were fused into one single superforce. As the universe cooled and expanded, this unified force underwent a phase transition, much like water freezing into ice. And according to the mathematics of these theories, this cosmic freezing should have created topological defects, stable, heavy relics trapped in the fabric of space-time. The most famous of these defects is the magnetic monopole. A monopole would be a particle that is just a north magnetic pole or just a south pole with no opposite partner. It would be a fundamentally new kind of object, and according to the theories, it should be incredibly massive, perhaps as heavy as a bacterium but compressed into a subatomic size, and absolutely stable, meaning it would never decay. The problem is devastatingly simple. If these grand unified theories are correct, then the conditions of the early universe should have produced magnetic monopoles in staggering abundance. Calculations suggested they should be as common as protons, one for every particle of ordinary matter. They should be everywhere, flooding the cosmos, their immense mass dominating the density of the universe and altering its entire evolution. We should be able to find them with relative ease, their powerful magnetic charge leaving unmistakable trails in our detectors. Yet, after decades of searching with increasingly sensitive experiments, we have not found a single definitive magnetic monopole. Not one. The universe appears to be completely devoid of them. This was the monopole problem, a major crisis for particle physics and cosmology. If our best theories of unification predicted these particles and the universe showed no sign of them, then either the theories were wrong or something dramatic happened to remove the monopoles from our sight. This is where inflation performed another of its cosmic magic tricks. Remember that exponential, violent stretching of space in the first instant. If monopoles were created just before or during the onset of inflation, that expansion would have acted like the ultimate cosmic dilution. It would have taken any monopoles that formed and flung them impossibly far apart, reducing their density to effectively zero within our entire observable universe. Imagine a single grain of sand on an otherwise empty beach that stretches for trillions of miles in every direction. For all practical purposes, from your vantage point, the beach has no sand. Inflation did not destroy the monopoles, it simply swept them beyond our cosmological horizon, diluting them so thoroughly that the chance of one being in our neck of the cosmos is vanishingly small. This elegant resolution turned a catastrophic problem for particle physics into a triumphant prediction for cosmology. The fact that we do not see monopoles is not evidence against grand unification. It is powerful, indirect evidence that a period of inflationary expansion really did occur, scrubbing our local universe clean of these primordial relics and leaving behind the smooth, monopole-free cosmos we observe today. Inflation solved the monopole problem by diluting them away, but its solution may have opened a door to an even more staggering possibility. The mechanism that smoothed our universe could have created countless others. This is Discovery 20, the multiverse hypothesis, a speculative but profound consequence flowing directly from the mathematics of eternal inflation. Picture the process not as a single, uniform event that stopped everywhere at once, but more like a pot of water coming to a boil. In eternal inflation, the repulsive energy field driving the expansion is not perfectly uniform. It has quantum fluctuations, tiny hills and valleys in its energy landscape. In most regions, the field rolls down into a valley, its energy dissipates, and inflation ends, converting that energy into the hot soup of particles for a new universe, a bubble like our own. But in some regions, a quantum jump might push the field back up the hill into a state of even higher energy. In those patches, inflation does not end, it reignites with ferocious intensity. This creates a self-replicating pattern. The overall inflating space expands so rapidly that, even as countless bubble universes like ours nucleate and freeze out, the regions between them where inflation continues grow even faster. The process never stops. It becomes eternal, giving birth to an endless froth of bubble universes within an ever-inflating cosmic sea. Each of these bubbles would have its own distinct properties, its own random set of physical constants and laws determined by how its local inflation ended. In this vast multiverse, our universe is not special or fine-tuned. It is simply one of an infinite number where the constants happen to allow for galaxies, stars, and life to form. This idea transforms the philosophical puzzle of why our universe seems so perfectly balanced for existence. It suggests there is no balance, only a staggering lottery where we naturally find ourselves in one of the rare habitable tickets. The concept sparks fierce debate. For some, it is a natural, almost inevitable extension of inflationary cosmology, answering deep questions about fine-tuning. For others, it is a step too far into the untestable, a theory that predicts everything and therefore explains nothing specific about our unique home. Can a multiverse ever be a scientific idea if we can never observe these other bubbles? Scientists grapple with this, searching for potential, albeit indirect, signatures, like a collision between our bubble and another in the distant past that might have left a scar on the cosmic microwave background. Whether a profound truth or a philosophical dead end, the multiverse hypothesis forces us to confront the ultimate scale of reality and the very limits of what science can ask about our cosmic origins. The multiverse offers a breathtaking escape from fine-tuning, but it forces us to confront a deeper, more intimate mystery right here in our own cosmic history. For inflation to have produced the universe we see, its parameters needed to be set with an almost unnerving precision. The energy scale of the inflationary field, the exact duration of the expansion, and the specific shape of its energy potential, the mathematical curve describing how it decayed, all had to fall within a remarkably narrow window. If the inflation had been even slightly more powerful or lasted a fraction of a second longer, the universe would have been stretched into a featureless, empty void, with quantum seeds stretched so thin that no galaxies could ever form. If it had been weaker or ended too soon, the universe would have remained small and crumpled, recollapsing under its own gravity before stars could ignite. The process had to be a Goldilocks event, not too hot, not too cold, but just right to create a cosmos that is both smooth and structured, flat and fertile. This exquisite tuning feels like a cosmic conspiracy. Why should the laws of physics and the initial conditions align so perfectly to allow for complexity and, ultimately, observers like us? This question has led some scientists down a philosophical path toward anthropic reasoning. The idea is stark: if there are countless universes in a multiverse, each with random physical parameters, then we inevitably find ourselves in one of the rare bubbles where those parameters allow for our existence. We are not seeing a tuned universe, we are seeing the only kind of universe we could possibly see. It is a cosmic version of the survivor's bias. You do not wonder why you survived a disaster if all the people who could wonder perished. For proponents, this dissolves the mystery of fine-tuning. It is simply a logical necessity. For critics, it feels like giving up on a deeper explanation, a retreat from the scientific quest to understand why our particular universe has the rules it does. This tension has spurred a parallel search for a more satisfying answer, a deeper physical principle that would naturally select the inflationary parameters we observe, perhaps from a unique mathematical framework or a fundamental theory of quantum gravity. Perhaps our universe's settings are not a random lottery ticket, but the only possible outcome of a consistent cosmic logic we have yet to fully grasp. The fine-tuning of inflation thus stands at a crossroads, pointing either toward a staggering multiplicity of unseen realities or toward a hidden elegance at the very heart of existence, waiting to be decoded. Yet the story of cosmic origins is still being written, and inflation, for all its triumphs, is not the final word. Competing visions of the beginning offer radically different narratives, challenging the very notion of a singular, explosive birth. One profound alternative is the cyclic model. In this view, our Big Bang was not the absolute beginning, but merely the latest turn in an endless cosmic cycle. Picture our universe expanding from a hot, dense state, just as we observe, driven by dark energy until galaxies are pulled apart. But then, in the far future, a mysterious transformation occurs. The dark energy field decays, and its repulsive push turns into an attractive force, drawing everything back together in a reverse of the Big Bang, a big crunch. Instead of collapsing to a point of infinite density, the universe passes through a kind of cosmic bounce, a transition where space is smoothed and renewed, leading to another period of expansion, another Big Bang. This cycle repeats eternally. This elegant idea naturally solves the horizon and flatness problems, not with a one-time stretching, but through the endless repetition of the cycle, which acts like a cosmic iron, smoothing out wrinkles and flattening geometry over countless iterations. Another challenger emerges from string theory called string gas cosmology. It proposes that before our familiar three-dimensional space existed, all dimensions were compact, tiny, and tangled. The early universe was a hot, dense gas of the fundamental strings of string theory. Through a thermodynamic process, only 3 of those spatial dimensions managed to expand and stabilize, giving us the vast universe we see, while the others remained curled up at microscopic scales. In this model, the uniformity of the cosmic microwave background arises not from superluminal stretching, but from thermal equilibrium in that early string gas, while the density fluctuations come from vibrations of the strings themselves. These alternatives remind us that cosmology is a dynamic, living field. The success of inflation is measured not by a lack of competitors, but by its ability to withstand their challenges and make precise predictions that others struggle to match. The existence of these other paths is not a weakness of science, but its greatest strength, a constant reminder that our quest to understand the beginning is a conversation, not a decree, and the universe may still hold surprises that rewrite the first line of its own story. The James Webb Space Telescope is staring into the cosmic dawn and seeing something profoundly unexpected. Its infrared eyes, designed to see through dust and peer back to the universe's first galaxies, are revealing a cosmos that grew up far faster than anyone thought possible. Instead of finding only small, fragile infant galaxies, JWST is spotting colossal, fully formed cities of stars that existed when the universe was only a few 100 million years old. These galaxies are not just early, they are massive, containing hundreds of billions of stars, and they appear shockingly mature, with complex structures and heavy elements that should have taken much longer to forge. It is like opening a family album expecting to see blurry pictures of a toddler, and instead finding clear, detailed portraits of a teenager. This discovery throws a wrench into our most sophisticated simulations of cosmic evolution. According to our standard models, gravity needed more time to pull together enough gas to form stars, to have those stars live, die, and explode, seeding space with heavy elements to build subsequent generations. The sheer speed and scale of what JWST sees suggests that the first seeds of structure, those quantum fluctuations from inflation, may have been more potent than we calculated, or that some unknown, turbocharged process of star formation was at work in the primordial darkness. These galaxies are not just rewriting the story of galaxy formation, they are sending shockwaves back to the very beginning. their existence and maturity place new, stringent constraints on the timeline of the early universe. They tell us that the Dark Ages ended earlier and more violently than we imagined, that reionization was likely driven by a ferocious first generation of stars and black holes, and that the raw material for building giants was in place almost immediately after the Big Bang. This forces cosmologists to ask new, urgent questions about the aftermath of inflation itself. Did the process that smoothed the universe also, in some subtle way, create extra dense pockets that collapsed into super-galaxies with breathtaking speed? The data from JWST is a time machine with a challenging message, showing us a dawn that was brighter, fiercer, and more brilliant than our most ambitious stories dared to suggest. The brilliant but puzzling dawn seen by James Webb demands answers that may lie in the faintest whispers of the universe's first light. Our next leap in understanding will come from two extraordinary missions, poised to listen to the cosmic microwave background with a sensitivity we can barely comprehend. On the ground, an international collaboration is building CMB Stage 4, or CMB-S4, a colossal array of over 500,000 detectors spread across telescopes in Chile and at the South Pole. In space, the Japanese-led LightBird mission will launch a satellite to scan the entire sky from the pristine quiet of orbit. Their shared, monumental goal is to map the polarization of the CMB with a precision 50 times greater than any previous experiment. This is not a simple upgrade, it is a quantum leap into a new realm of cosmic perception. Their primary target is the holy grail we have hunted for decades, the primordial B-mode signal from gravitational waves generated by inflation. The difference now is raw power. These instruments are so sensitive they could detect a temperature variation equivalent to spotting a single grain of sand on a beach that stretches from Earth to the Moon. With this power, they will either finally capture the definitive swirls in the CMB's polarization, giving us a direct movie of the universe's first violent tremor, or they will rule out entire classes of inflationary models, forcing a radical rethink of cosmic beginnings. But their ambition does not stop there. By measuring the CMB with such exquisite detail, they will also weigh the ghostly neutrino. These nearly massless particles flooded the early universe and subtly affected how those primordial sound waves propagated. CMB-S4 and LightBird aim to measure the total mass of all neutrino species, a fundamental property of nature that has eluded precise measurement for a century. Furthermore, they will search for the imprints of entirely new, unknown particles that may have existed only in that first searing instant, particles that could be the key to unifying gravity with quantum mechanics. These are not just telescopes, they are time machines tuned to the first trillionth of a second. They represent humanity's most determined effort yet to read the fine print of creation, to move from a compelling story about our origins to a proven, detailed history. The data they will collect in the coming decade could either cement our current cosmic paradigm or shatter it, opening a door to physics beyond our wildest imagination. These discoveries are more than a collection of facts, they are a mirror held up to our own existence. Each one, from the quantum seeds to the accelerating void, has systematically reshaped our understanding of reality, moving cosmology from the realm of myth and philosophy into the domain of precise predictive science. We no longer tell stories of gods balancing the world on a turtle's back. We write equations that can predict the temperature of the sky to a millionth of a degree and trace our lineage back to a microscopic tremor. This journey from wondering to knowing carries a profound philosophical weight. It tells us that the universe is not just vast, it is ancient beyond true comprehension, nearly 14 billion years old. It is complex beyond belief, woven from dark threads we cannot see and driven by energies we do not yet grasp. And we are here in the briefest flicker of cosmic time, on a pale blue dot orbiting an unremarkable star, and we have managed to piece this story together. The atoms in our hands, the iron in our blood, the calcium in our bones, were forged in the hearts of stars that lived and died long before our sun was born. We are literally stardust given temporary consciousness, and that stardust now contemplates its own origin from a quantum fluctuation stretched across an infinity, in a geometrically flat universe that should not, by any ordinary logic, exist at all. This is the ultimate impact, a deep and humbling awe. We are not the center of the cosmos, but we are its mind, a way for the universe to know itself. The great cosmic machine, through 13.8 billion years of expansion, cooling, and evolution, has produced beings capable of looking back and deciphering the code of their own creation. That ability transforms the cold equations into a narrative of breathtaking connection. We are not separate from the universe, we are its most recent, most fragile, and perhaps most remarkable expression. To know that we are the universe becoming self-aware is to find a new kind of place in the grand scheme, one built not on privilege but on participation and profound wonder. From a faint hiss in a New Jersey field to the brilliant galaxies seen by James Webb, our journey has spanned the entire history of the cosmos. We have traced a direct line from the accidental discovery of the Big Bang's afterglow to the theoretical brilliance of cosmic inflation, from the quantum seeds of all structure to the dark energy shaping our future. These 25 intertwined discoveries are not separate facts, but chapters in a single, epic narrative. Together, they have given us a coherent and remarkably detailed origin story for everything we see, a story written in light, gravity, and the fabric of space-time itself. Yet for all its triumphs, this story remains gloriously incomplete. The Hubble tension, the lithium problem, and the breathtaking early galaxies are not failures, they are guideposts. They are the universe's way of pointing toward the next frontier, the next layer of mystery waiting beneath the one we have just peeled back. This is the essence of science and the beauty of our human quest. We are the part of the cosmos that has awakened and begun to ask questions of its own birth. We listen to echoes from the first trillionth of a second and build telescopes to see the first dawn, driven by a need to understand our place in this vast, unfolding reality. So we turn this final question to you. On this journey from the quantum foam to the cosmic web, which single discovery reshaped your understanding of reality the most? Was it the perfect blackbody curve, the quantum origin of galaxies, or the accelerating fate written in dark energy? Let us know in the comments below. If you want to join us as we explore the next great cosmic mysteries, be sure to